So thank you everyone for coming. Please enjoy some cookies and muffins and eat chips quietly. Uh, but yeah, thanks for coming. This is my PhD dissertation defense, hopefully the only one. And so I did this on the manufacture of infrared optics and brittle materials. We've thought about adding the word freeform in here with the word optics, but because that's one of the main things we're focusing on. But I thought we'd leave it a little more general for now. But some of my committee members, my committee chair, Dr. Matt Davies, committee members Evans, Schmitz, and Slesky, and the graduate school rep, or another committee member, however you want to think of it, as Dr. Angela Davies. So thank you for being here. So the motivation for my dissertation is freeform optics, as I just said. Freeform optics are set to revolutionize the optical design space with new optical functions, light management, reduction of components, introduction of alignment features and mechanical and metrology, as well as biomedically inspired optics like the moth's eye or the mantis shrimp. Also, freeform diamond machining is an enabling technology for infrared optics because many IR materials are diamond turnable, diamond machinable, and the tolerances are a little more relaxed, which makes it easier for you to make the optics. And when you get into visible, you worry that the diamond turning machines aren't accurate enough, aren't controlled enough to reach the tolerances you need for visible. So several challenges we must overcome are understanding how to machine the brittle materials, whether you're turning or milling or however you're doing it, and also error correction. And the error correction we're going to be working on is tool error correction, and putting that into software to generate your toolpath to make freeform optics. And last is metrology. I'm going to be focusing on the first two. I'm not worried about metrology as far as how to make them, not yet at least. Hopefully in the coming semesters we'll figure out the metrology. So I'll be focusing on the how do we machine the materials, and then once we know how to machine the materials, how do we make a freeform optic that we expect to be in tolerance? How do we correct any errors we expect will be in the part before we machine the optic that we don't know how to measure? So why freeform? So I've got a couple of examples here. This one here is an example of light management. So a typical gas station at night, the lights are many direction light. You're wasting a lot of the light energy out here where people aren't going to be. So if you wanted to focus all of the light right where it needs to go, you could put freeform optics in. So now all the light, you wouldn't even need as bright of a light to be able to illuminate all the area that was necessary. So that's just a quick example of light management. Some examples here that we've done here at UNC Charlotte. We've got an example of an Alvarez lens, where an Alvarez lens is two separate cubic surfaces facing each other, the same prescription, and when sheared sideways, you start with what would look like a plano flat lens, and when you shear them sideways, you turn it into a focusing plano sphere shape. That would be the approximation of what the light is doing when it goes through. I see some grins.
I was waiting for you to tell me whether that was a plano convex or a plano concave.
So that would be So you go one direction, you get a negative power or a plano concave. If you shift this direction, you would get a plano convex or a positive power.
Our test setup's only set up to measure that at the moment. So.
Yeah, so the optic that I'll be describing later that we made, we designed it to be just 0 power to positive power. We didn't need to make the portion of the lens to do the negative power because we can't measure it right now. We can't characterize it. And then a piece that goes along with freeform optics, you can think of them as freeform optics as well as a multi-scale optic. So we've got a moth's eye, where a moth's eye is on the millimeter scale. If you just look at one, it looks like a millimeter size spherical looking lens. If you SEM, you get these small micron size little lenslets. And on each one is nanometer scale structures. The purpose of these structures here for a moth's eye are anti-reflection. So can we create surfaces like that in infrared optics that could be anti-reflection without having to do coating? And here's an example of mantis shrimp eye, where I believe it also has some anti-reflection, but also these one-directional structures on here create a polarization sensitive imaging as well, so they can actually see polarization from different polarizations and different types of creatures and other underwater things that may be an enemy, maybe food, and they give off a different polarization signature. And the mantis shrimp is able to distinguish between the two. So these are sort of the inspiration, freeform optics and multi-scale optics for the work I'm about to discuss. So the outline, I'm going to be talking about two different materials that we've worked with, chalcogenide glass, specifically IRG26, germanium, and then also the tool error correction. So in the IG6, we're going to be discussing orthogonal cutting, facing, which would be a typical diamond turning operation we'd be facing, and also ball milling. In germanium, we'll be talking about, or I'll be talking about round nose and dead sharp ruling or planing, and orthogonal cutting also in germanium, and the effects of the crystal orientation in germanium on the force measurements for both the ruling and for the orthogonal cutting. And then tool error correction, where are the tool errors coming from? How are we going to correct them? And then the process for generating the tool path and doing the error correction. And I'll finish that off with a couple of lenses that we've made and some surfaces we've made for application. So scientific background for a few decades now, and even further back than that, we have examples of machining of what would normally be considered a brittle material, something that if you tried to cut it would fracture. We've got examples in literature of with specific parameters, geometries in the cutting, you can achieve what would be sort of thought of as a more like a metal type cut, where you get a curly chip like this, or like this, where there's debate right now about what to call that. So I'm going to be calling this either ductile mode machining or ductile dominated cutting, something of that effect, or brittle machining, brittle mode. I'll be using those words. There's some people that may tell me that's not correct, but I'm defining them as that right now. If you can get a curly chip, I'm calling that ductile mode or ductile dominated machining. So in the 80s we had an introduction of, by tipping a tool forward and creating what's known as a negative rake, you can get a curly chip in what would have otherwise been a fracture dominated cutting operation. In the late 80s and early 90s, we also have coming out where this was separate ruling features in sodium lime glass and another visible transparent glass that we typically think of as needing to be ground and polished. We see cutting resulting in a curly metal looking type chip. Same thing here, Blake and Scattergood. There's a handful of Scattergood papers that relate fracture mechanics from NIST presented by Lon, where they're relating indentation to diamond machining. And Scattergood developed this critical chip thickness at which so along here fracture is being created, and at the critical chip thickness the resulting fracture would be shallower. This one is shown as being just below, but the critical chip thickness would be at what thickness is the first fracture created left on the surface when you finish cutting. If all the fracture occurs above the final surface, you don't care about it, as long as none of the fracture makes it to your surface. And then actually, as I'll show, having some fracture up here can actually be beneficial as long as it doesn't make it to your surface. And then Luca and Haken, using a machine called the NanoCut that was developed and made here at UNC Charlotte, they did planing experiments with a very large radius tool to simulate an orthogonal cut. And they went through a variety of rake angles and looked at how that affects the force and how that affects the when the surface fractures. And they introduced this concept of watching the resultant force on the material as it rotates. So I didn't show the figure, but as the cutting force gets higher than the friction, or if you're doing a negative rake, it would be the normal force and the friction force. But when the cutting force gets higher than the thrust force, that's at the point where the resultant angle is at 45 degrees on the surface. And as it rotates the other way, you actually start creating tension on the surface. You're actually pointing more towards the normal and forward, as opposed to pointing straight into the part. You're pointing more forward and creating tension on the surface you've already cut and fracturing behind you. So that's a current debate right now, or something people talk about is the fracture occurring behind the tool, or is it occurring in front of the tool? So we're not necessarily going to answer that question, but that's currently what is being discussed. So my thesis, I'm going to start with the chalcogenide glass. As I said, the glass that we selected for these tests, or was selected for us, was IRG-26. It's a material made by Schott. It's got relatively good transmission through a fairly wide infrared range. So where we're focusing our work on is making optics in the thermal range. So down on this end, we've got relatively good transmission through the 8 to 12 micron wavelength. Also, the reason why this material was so sought after is the glass transition temperature, the temperature at which the material starts to deform, even under its own weight, is 185 degrees Celsius. So this leads to molding capability. So can you mold infrared optics as opposed to diamond turning all of them? So, but we would like to prove this material can be prototyped with diamond machining. So we start with orthogonal cutting. So orthogonal cutting is taking a more complex cutting geometry and reducing it to two orthogonal direction cutting forces. The only forces that are non-negligible are in the feed direction and into the board in this image right here. So you just have two directions that you have to look at. You don't need to worry. We measured them and showed that, well, we knew from the measurements that the forces sideways were in the less than 1% compared to the other two, or it completely covered by the noise. So we've got a dynamometer for measuring the force. We used a 60-degree dead sharp tool, rotated so that the front of the tool, the leading edge of the tool, is flat and perpendicular to the feed direction. And what that does is it creates a constant chip thickness along the width, all having the force going perpendicular to that. So it creates the most simplified geometry, where we can just investigate what is happening due to the chip thickness, and then we could adjust the width, and all that should do is scale the force linearly with the width. So we picked a width of 200 microns, and we kept that fixed through all the testing. We did a couple at 500 just to show that yes, it was linear, but I'm not reporting any of that here. Spindle rotations this way. So this is sort of the simplified geometry I was talking about. We got with a zero rate configuration, we got a cutting force and a thrust force. And I said 200 micron chip width. We did chip thicknesses from 100 nanometers to 8 microns, and we tested some speeds from 1 to 8 meters per second. And all of our data sampling was done at 5 times the natural frequency of the dynamometer. This is also the same basic setup that we're going to use for germanium as well, with just one minor change. Well, maybe not minor, but one change. So here's the initial test results we got from the orthogonal cutting. So these forces obviously are scaled with that chip width. So we've got our cutting forces and our, sorry, that should be a T. Shadow puppet, T. So we've got our cutting force, and the blue is our thrust force. And then here we've got what's called the force coefficient, is the force per unit area. So that's a number you can use. You find your chip area and you can use that to calculate what your force is going to be. Typically in metals, this force coefficient is relatively flat, or constant through a range of chip thicknesses. As we're finding here, as we change our chip thickness, we have a pretty significant change in forces, or a pretty significant change in our cutting force coefficient. So what we saw, I started, the sequence of these cutting tests was from left to right. So we started with the smallest cuts, which we assumed would give us ductile dominated, fracture-free, ductile dominated cutting. And as we increased our chip thickness, our force increased as we expected. But then this points at 900 nanometers. When we went from 900 nanometers to 1 micron, it all of a sudden dropped significantly, much more than we would have ever anticipated. And then the force no longer goes at this angle. The slope no longer, it's now a little less steep. So this drop here, we've theorized is related to what was ductile dominated and what's become brittle dominated. So we found some chips from this test and from this test here. And the chips here, we see these curly 200 micron long curly little shavings. So this is something that I would expect to see when you're like sharpening a pencil or something. So nice and curly shavings. And then here, I looked all over trying to find anything that looked like this for these chips, and all I found was sort of pieces that look like gravel, and sort of have like that stereotypical like fracture, like striation marks. I don't remember what they're called, but so brittle and ductile dominated. So we've got cutting forces up here that are in the let's see. So this is aluminum. So these numbers up here are in the like more mild steel type numbers, and then all of a sudden it drops, and we're getting numbers more like plastic. So we've got these really low forces. This is what I was talking about. If you've got brittle fracture happening up along your turning tool, you can reduce the force to cut as long as they don't go into your surface. You don't care about that. So the thing that I want to point out is when we go from this test to this test, it doesn't happen instantly. There's a transient force that occurs. All these data points are steady state. So I took an average of an entire 80 revolution test, and that point is the average of that test. So if there was any big jumps throughout the test, I threw away that test and kept repeating the test until I got 3 consecutive steady state forces, and that's where these points come from. But if we look from the last test here and the next test cutting at this parameter, we see a force that we would expect to see if we followed along this trend initially, and then a drop to what we then see continuing through here. So this is what we believe is the ductile dominated, and then as fracture begins to occur, it propagates, and then this is the state at which the brittle fracture has reached the most fracture that it's going to get, and it just stays at that level.
That's again over about 30 revolutions.
Yeah, so this test from here to here is 80 revolutions of data. So this is happening over full cycles of cutting. It happens quick, but it's still about 30 revolutions of data to get. And this transition it wasn't always 30 revolutions of data to get to constant, to get to a steady state. This varied on how big of a jump we made. If I went from here to here versus here to here, and if I tried to go backwards, I would get a different drop or a different rise. So the next thing we wanted to look at was, so we now know we've got a change in cutting force coefficient relative to chip thickness. Now we want to see is there a speed dependence? Are we seeing at different RPMs, at different cutting speeds, are we seeing a change in force? And at the range that I'm showing here from 1 to 8 meters per second at a constant chip thickness, a constant chip width, we're not seeing any noticeable change in speed. So this was one of our first speed dependent tests we did. We saw this and said, okay, there's no speed dependence, and we moved on. There was a weird point we saw here I'll mention later, but it seemed inconsistent with the data. And we moved on to further investigating the non-speed dependent, just fixing the speed. So I thought to myself, okay, I did the sequence from left to right. What happens if I do it right to left? So I started with a brittle surface, or what I say brittle surface. What I assume is brittle fracture dominated surface, because we cut the material away every time. So inspecting the surface each time is would be time intensive and would be longer than what would be worth taking these tests for. So I start working my way this way, and instead of jumping from 1 micron up to the 100 nanometer here, I stayed down here. 900, 800, and at 700, I jumped. So if we zoom in and look at this, if I'm coming from the left, I work my way up this side and then drop. And if I come from the right, I come this way and then up. So the way I explain this is the propagation of fracture. If the surface is already fractured, it cannot get through the fracture without pushing the fracture even deeper, until it reaches some chip thickness that just does not want to fracture. It doesn't propagate fracture is what I mean. So in these cutting conditions at 700 nanometers, it would not do anything but forces up here. Could not force it to be fractured. But at 800 or 900 in here, it would depend on what the surface was before. So here's a couple of tests that kind of show that and show the transition I was talking about. So here we've got a point down here in this 800 nanometer or 0.1 micron. We've got down here. So this is what I'm calling brittle dominated. And then I step back to 700, and this one takes about 80 revolutions. So it took almost 3 times longer than the last one I showed to get up to this force here. And then it remains there. I work my way back. And then this was a little ways into the testing. So we believed that the tool edge was wearing on a nanometer level, and that's why at 900 for this test we started to drop the force down to a steady state that we would expect to see down here. There's also some concerns that the IRG-26 isn't completely homogeneous, so there may be some material dependency as well throughout the sample. But lots and lots of tests were repeated, and this 900 to a micron, 900 nanometers to a micron was the transition throughout all of our testing. But this was 320 revolutions of data just to get through to a steady state. So now we take these results and we want to see how they compare to facing. So we did a typical facing where at the lower parameters here where we expect to see good ductile fracture-free surfaces, we get in the nanometer range surface finishes. Up at a 10 micron step over, we're getting heavily fractured surfaces. So now we want to use our orthogonal cutting results to predict those forces. So we take the geometry of the cut, and then we calculate the chip thicknesses along here. And the way I did it is I picked the point here and found the minimum chip thickness everywhere along the tool, and then do a numerical integration by multiplying this chip thickness and this dx is my change in width. Multiply that by the cutting force coefficients that I found in the orthogonal cutting. And so here I'm sort of mapping this transition depth that we think that we're going to switch between ductile and brittle, and the maximum chip thickness along the chip and the average chip thickness. So from this we expected somewhere around the 5 micron feed per rev that some brittle fracture would be occurring. But at 2, everything should be below that transition depth. So this is the predicted forces here. We start to see it drop like we were expecting. When we compare it to the facing results, we see that there's a bigger drop from 2 to 5 than predicted by our orthogonal cutting model. So this is when I had gone back and found that hysteresis. So I went back and put the forces from the bottom of the hysteresis, where we're working our way from a fractured surface back towards, or fracture-dominated cutting to ductile-dominated cutting. And the trend better matches the forces that we're seeing. So the way that I see these results is when we're turning, fracture's occurring up higher, and that fracture is sitting right next to where there's not fracture. And since we've got this hysteresis, the fracture is going to sort of propagate its way down the tool. And then when we get to a thickness, which I'm assuming is around 700 nanometers, the rest of it will continue to be ductile, but the fracture is going to propagate all the way to that point. So it makes sense to use the bottom side of that hysteresis curve for our force coefficient. So next the ultimate goal for this project is to understand milling. So we did some empirical milling tests to see what sort of surface finishes and fracture we're going to get. So we did a grid of parameters and we only found fracture on the most aggressive feed per rev, and we only found the fracture in the first cut, which would have been a full slot cut as opposed to cuts just being on one side. So this was seen in every single step over. We found fracture just at the beginning. So if we take surface finish measurements and compare it to the ideal surface, we follow the trend. When we get down here, the machine ends up becoming our enemy in our surface finish. So we've got some drift, the milling spindle's kind of moving around a little bit. So the surface was apparently fracture free, but we're still seeing a slight increase in surface finish, but still following along this trend. And if you zoom in here, you see some slight changes. These are the different feed per revs for the step over, for that one step over. And this is the shape, the theoretical shape we would see for a perfect tool, a perfect machine, synchronized chips as we moved along. And the standard deviation of these surfaces is within a few percent of each other. These are all the same Y or Z scale. That's why I didn't make any attempt to zoom in on them. But the PV is almost double the PV of this, but the standard deviation, because these points represent such a small fraction of the surface, it's heavily dominated by the stuff that's down below that's similar to this. So I just thought that was interesting. We also tried variations of rake angle and milling spindle inclination. So I've got here, you can rotate the milling spindle to have where the rotational axis is no longer normal to the surface. So we saw negative rake tool had the least amount of fracture, and the zero rake tool with zero milling inclination had the most fracture, but this surface here showed re-adhered chips. So it appears that with the negative rake, we're sort of smearing the chip in front of it back into the surface. So this is not desirable. And this setup right here is the easiest for software correction as well. So this ended up being the configuration that we used for all of our making our parts. So next we've got germanium. Same Kistler dynamometer setup. We've got a round nose tool used for ramp in, ramp out tests while taking force measurements. This allowed us to see where fracture occurred on the surface after the test. Same with the spiral ramp in, all non-overlapping cuts. And then the dead sharp grooves, which would be the ultimate goal of this work, would be to produce these multi-scale, these small scale structures. So we've got some dead sharp groove results in here as well. So if we take this is a ramp in, ramp out where the final depth is 1 micron. You can see here where this is fairly filtered. I've got the description up here. But as the force comes up around the time that it starts to
Back you up a little bit. So you switched to planing operation in
Yes.
germanium and
Yes.
not orthogonal cutting, so even simpler than in some ways simpler than orthogonal.
So we were using a tool that is more like a tool we would be facing with. So a typical tool that we'd actually be cutting with. And we wanted to see, we weren't expecting such a change in chip thickness as it relates to our force. So we started with these round nose tools. This allowed us to see somewhere around this region right here where fracture is starting to occur, our force starts to fluctuate quite a bit. The biggest fluctuation in force, this big dip right here, occurred with a fairly sizable pit, a big fracture in the surface. So that was pretty interesting. That sort of let us know, okay, when the surface is fracturing, it causes the force to drop. And then we came out the other side. Evans pointed out when I presented this originally that should this have been symmetric, or would we have expected this to propagate more into the surface? We were talking about that, and we believe that the surface prior was non-fractured. So if we recut on top of this, I would expect the brittle fracture to go a little bit further this direction than the other side. Satisfied?
Yeah.
So now we need, if we're trying to calculate our force coefficients, we need the area of the cutting. So we, from our depth of cut and our tool radius, we come up with our the chip area. We now take our force divided by the chip area, and we plot our cutting and our thrust forces. So this region right here corresponds to that well-behaved region that we saw in the round nose cut, where we saw very, very little fracture here, but no fracture further down. So we've got a nice, relatively flat cutting force coefficient, and then our fluctuations start to increase. So what was interesting to point out here was if we assumed this cutting force coefficient through the entire test, we would have expected a straight line to follow this red line and back down. It's interesting to note that this is unfiltered, none of the force exceeds where we would have expected this behavior to continue. So the way I see that as when this tool hits a pit or breaks a chunk out, the force drops, and then immediately after that it may not fracture quite as bad and we get a spike back up. So we're getting this fluctuation, but never exceeding sort of what we would have expected from a purely ductile cut. So we wanted to more simplify the germanium cutting operation. So we went to this orthogonal cut. Same setup as the IRG-26, but I included this adapter plate to induce a negative 25 rake angle. So same size tool, it's a different tool, but it's the same shape and everything as the IRG-26. We just put this negative rake. And now we worked with a slightly wider range of chip thicknesses. We went a little bit smaller and went through a range of speeds as well, negative 25 rake and a constant chip width of 200 microns. So here's the results from the germanium at a constant speed of 4 meters per second. That's where we did the RG-26. And we don't see that drastic drop-off that we saw in the RG-26. So it's still not completely clear why the RG-26 is dropping so drastically, but we do see the force start to kind of level off a little bit. So this tells us that if it's acting like the RG-26, we're starting to get more brittle fracture out here, so the force is leveling off. It's kind of difficult to see 3 orders of magnitude, so I put it on a log scale, and this transition right here, when the thrust force drops below the cutting force, I believe is the edge radius of the diamond creating what they call a increased effective rake angle. So if the cutting edge the radius of the cutting edge is bigger than your depth of cut, then it just, to the surface, it just looks like a big negative rake. So that's why we see this huge spike in thrust. As the negative rake increases, you see a higher thrust force that's pushing against, the tool has to work harder to stay in the cut, is what that means right here. But then the cutting force coefficient doesn't continue increasing. It sort of levels off in this range here. So that's what we see there. So, but after this, I don't know, put on a log scale. It looks flat all the time, but we're getting in the ruling or the planing, we never drop below about 5,000. The force coefficient never dropped really below 5,000. In the orthogonal cut, we're seeing significant amounts below. Now we did go higher, higher chip thicknesses in here, and this does seem to still keep going down, but the drop is much less severe. The reason for that is with the round nose tool, we have every chip thickness from 0 to our maximum chip. So we're taking force coefficients from this orthogonal diagram here, and we've got higher, not necessarily higher forces, but force per area is greater here than it is here. So it seems like it would make sense as you continue getting deeper, you still have a 0 chip thickness. So we're still working in this range, no matter what you do with a round nose tool. So the orthogonal cutting seems to give us more information about what the actual cutting mechanics are. So now we move to, is there a speed dependence in germanium? So I picked a constant chip thickness of 200 nanometers, again 200 micron chip width, and I swept through a similar range of speeds that we did in the RG26, found a 50% drop in force from a 0.25 meters per second to the 4 to 8 meters per second range. A fairly big drop of force, where when the RG26 we saw relatively level, just small little bumps but no trend. So we said, okay, well let's try a different chip thickness. So here's 500 nanometers. Again, the same thing. So obviously it seems there is a speed dependence in germanium. We did the calculation for at what amount of energy you put into the surface could you potentially melt germanium. And the numbers were surprisingly similar to if we assumed a 20% of the heat stays in the chip and 20% of the force you put into the surface causes heat in the chip. We were getting numbers around the melting temperature of germanium. So it's at speeds up here. So it seems possible that we're actually sort of, maybe not quite melting, but we are certainly getting close to melting and causing the force to drop. It would be really interesting to know what the surface looks like at these different forces. Was this a fracture, less fracture, and this was more fracture, or was it all the same? Or so that would be something interesting to for a future student to work on. And here we've got them combined together. And so for an example, here's the cutting force of aluminum with a 500 nanometer chip. So we're a good bit above that, but still surprising that we ended up down near aluminum, where when germanium was showing us numbers, when we were doing the round nose ruling, we were seeing numbers more like hardened steel. So it's interesting, we go a good bit faster and our forces drop quite a bit. So here is all of our chip thicknesses that we measured and 2 different speeds. So when we're in that range, we've got this extreme negative rake. We're not seeing much variation between the speeds, but once we leave that 50, 60 nanometer range, we see a pretty big deviation as we work our way along. We thought this was going to happen, but it was still pretty exciting to see it actually happen, because this 4 meters per second is typical milling speeds when you work your way up along the diamond. And so 4 meters per second on a 1-inch diameter part was like 4,000 RPM. So you can turn at that speed, which obviously we did, but it's not, you wouldn't always run at speeds like that. So now I want to show the crystal orientation. So this is results from the round nose planing that we did. Horiyuchi showed in his paper this 3-fold symmetry that you see in germanium when you turn it. You get 3 sections that show significant fracture before these regions would show fracture. Again, if you go more aggressive, eventually this will start to fracture, but these 3 regions will fracture first. And we saw that as well, and we wanted to see, do we see that in the force? So here's one of the spiral tests, and if we zoom in on what looks like noisy signal, it's actually this 3 per rev fluctuation in force as we work our way around the surface. And if we look, I've put these red lines here to show radially that this and this line are at the same point. We don't see fracture here, here, or here, but we see fracture in most of these along here. If we zoom in on that, no fracture. We start to see a couple little pits here, but we see a significant fracture showing up here. This was about 150 to 200 nanometers different in maximum cutting depth, or chip thickness, just by changing the crystal orientation. So when I look back at the orthogonal cutting, I averaged all of this to get one data point. But if you come back and look at it, what's actually happening is this crystal orientation, and we're getting a pretty big percentage of force change just due to crystal orientation. And if we take Chris's standard bucket averaging, and we go 3-degree buckets all the way around, this is what we get for this cutting parameter. This was 200 nanometer chip thickness, and cutting force and thrust force. And the first thing that I noticed when I pulled this up, well, you kind of have to optimize the speed because the speed wasn't perfect. So this kind of smears a little bit, but when you get this just right, you see the phase lag between what appears to be the bottom of the forces, and the top here lines up with this one, but not with the middle. So it's still unclear why the thrust force would be, say, low or higher as the cutting force gets to its minimum. So that's kind of interesting. And then 4 different chip thicknesses, just looking at the effects of crystal orientation. This feature right here is something Horiyuchi mentioned in his as well, where at the best fracture-free region, there's this tiny little band right in the middle that will actually start to fracture just before the surrounding area does. So that's what we're seeing here. We're seeing this drop in force starting to occur in that 400 to 500 nanometer range. So that's very interesting and corresponded with results that we've seen in literature. And then here are some dead sharp ruling examples. I've got 1 micron spacing. These were in the 200 to 300 nanometers deep. This one was programmed around one micron. I expect it was probably closer to about 500 or 600 nanometers. The only difference between these 2 cuts is the crystal orientation. Just exactly like I'm showing it, 90 degrees from each other. This I had found was the best region to do cuts, and this was the worst. Yep. So the last thing to talk about is the tool error correction. I'll try to go through this quickly. So we developed, or it was developed the artifact-based. This procedure's been used for turning in the past, but we said that we wanted to apply this to milling. So you take a spherical artifact that you are going to cut, which is something that you can easily measure on a phase shifting interferometer, and map the tool errors on the tool. So here's just a couple of examples of we cut a sphere with no correction, and then we made a change to the tool path. It didn't necessarily make it any better, but we made a change to the tool path, and we saw a change in the form. So that lets us know that things are happening by adjusting the tool path based on tool shape, based on tool geometry. So this is the artifact-based. The 8mm radius of curvature, 8mm clear aperture results in a tool measurement of 0 to 30 degrees of the tool. The full angle across this is 60 degrees, but you're only cutting with one side of a turning tool, and with a milling tool, it's sweeping around. So you're going to map 30 degrees of the tool onto this surface. And we did this in germanium, IRG26, and brass. So the programming for this, how we generate the code and how we error correct, we start with the equation. We start with the equation of the sphere. We take the partial derivative, turn that into what is the surface normal at every point on the surface. Now we take our tool radius and offset it that distance in the direction of the surface normal by our tool radius. So here would be, as we work our way along the tool would be shifting in the direction of that unit normal by the tool radius. We would then cut a sphere, get an idea of what the error correction was. So the red would be some error that we found on the tool, and the direction of the arrows and the magnitude is how much correction in the unit normal direction would we need to make to correct for the waviness of the tool. And then we would take that tool with an error and the tool path that we would like to use, generate a simulated surface, remove the form, and then filter out surface finish, and we should get a nice flat at 0 surface. So this is with a coarser finish because the time to generate this was like 15 minutes. The time to generate one that would actually make you an optic was like 2 days. So we can filter this and get it flat. So that was the way we went. So the tool errors that we're seeing, we've got the mill and spindle inclination angle. That's not necessarily an error that we were looking at, but that is something that you would need to know. You would measure that. Then where is the diamond? Where is this circular shape positioned relative to the axis of rotation? If the center of the circle isn't on the axis of rotation, then when this rotates, you will not create a spherical ball shape that you thought you were. And then also on top of that, we've got the error from the optimum circular profile, which we call waviness. So what does what I call a radial shift, what does a diamond position error look like? What does it do to the surface? So we could have the diamond too close to the middle, where it needs to be, or too far out. So if it's too far out, and we cut a concave sphere, we'll get what's referred to in industry as an M. If we sweep through past, we get no error. If we go the other way, we get what's called a W. So an M or a W, this is in the diamond turning instruction manual from the diamond turning company. So this is the typical thing we were expecting to see, but this is done in turning. So we want to apply this to milling. So here's just an example where we put the tool in, no correction. If we average around or display all of the data points with the radial distance out from the center and then that error, we get this shape here. So at first glance you may not think that's an M or a W, but it's actually a W with waviness superimposed. So now we need to correct both of them. Independent is the wrong word, but we correct them one at a time. We optimize for one and then we correct the other. So if we take the blue line as our original, the green line is once we remove the error from tool position, the diamond tool position. We've corrected for the radial shift and we get the green. That's the residual. Go on.
Just to double check, the units are microns, not millimeters, correct?
No, this is millimeters times 10 to the minus 4.
Oh, okay.
Yeah, we said the exact same thing 2 hours ago, and then we found that. So we have our W. Let's see if it crashes again. All right, so now what's left over is waviness. So we've removed our tool error position, our radial shift. This is what's left. So what I did is I plotted the normal angle that we're seeing on the surface, which corresponds to the normal angle on our tool where it would have been cut. And I'm plotting the height error that we're seeing. And then for this one I use an 8th order polynomial. I need some way to represent the waviness so I can take it from this surface here and apply it to the tool in another program. So I need to some way tie them together. So I use an 8th order polynomial. If you go higher than 8, you start getting these like funny little tails at the beginning and the end, so I stopped at 8. That seemed to represent the shape that I wanted. The rest of this is mid-spatial errors that we're seeing on the surface that are not correctable by this technique, and are not tool errors. So we take this shape, that's the error of our tool, like I showed before, and the arrows point towards the direction of the correction. So here's the original. Here was after we made the correction. So we went from 300 to 60 PV nanometers for the averaged, I don't know what you call it, averaged in the theta direction. So here's MATLAB simulation of what's before and after. This little tail here is due to the fact that the data density near the center is much less than at the edge. So if you do a fit to this, it's much more heavily weighted at the edge. Now we've figured out how to cut the materials, and we've developed the software to make them to control the machine. So the first thing we decided to make, or was decided for us, what we were going to make, is something that could be measured. Can we use this technique? cut a surface that can actually be measured in industry. So we picked an A-sphere. Not only can the surface be measured, but it can be functionally tested. So we front and back our A-spheres. This is a landscape lens. So one lens and a detector can thermal image. Actually, I don't think I put pictures in here of it thermal imaging, but it can. We've got some pictures of the guy that designed the lens up in Rochester. So we use the technique that we've been talking about. So our technique can create a relatively arbitrary surface. This doesn't show that capability, so we wanted to show to everybody, with this technique, you can do something. You can make a rotationally symmetric lens that you could do by turning, and we're going to add a feature that you can't do by turning. So we've got, I think these are 45-degree V grooves, 35 or 45-degree V grooves. Getting a turning tool to get down in there to make those would be pretty difficult. Not impossible, but difficult. So we added these to sort of show if we had two optical elements that had some very specific distance between the two optics, which is typical, can we machine these optical tolerance level features that, so this is 3 grooves, can we put 3 balls on another optic, seat them together and have them have in the 100 nanometer range tolerances where what I typically see between 2 lenses, they're looking at like a couple microns, not a couple 100 nanometers. So with this, we could perceivably achieve optical level tolerances in assembly without needing to measure while we did the assembly. So that's why we stuck those features on there. Here's the machining video of it running. This is running at 12.5 millimeters per minute material removal rate. And then the last one's going to be the other side, but I'll go ahead and skip ahead. So the next application we use this for is, I talked about this Alvarez lens. So we, a student here at UNC Charlotte designed the Alvarez lens that we wanted to make that the nominal zero shift would actually have some positive power, and then you shift one direction, you go to a plano-plano, you go the other direction, you get an even stronger power than you had at the nominal. So we want to make this Alvarez lens. We've made ones here before, and we wanted to add these metrology fiducials that could be used when you measure the freeform. You could also measure these 3 features and use them as 3 points to define the coordinate system and the rotation. Flatten it and define the rotation. And these were made with the same parameters, the same type of tolerances that we're going to be seeing when we're making these. So start with your solid model. We've got these surfaces in MATLAB as well. Generate the toolpath, make your blank, machine your optic, and hopefully end up with a nice pretty looking optic. As of right now, these have not been functionally tested. We haven't done this testing. Some additional features need to be put on these to put them in the current fixture that we've got, but one of these in IRG26 and then one made in germanium have been sent out to be supposedly round robin measured, but I think they got stuck in Rochester, maybe due to weather. So we presented this at a conference, and the optics people were like, yeah, whatever. Who really cares about this? So we were a little disturbed and wanted to show this really is the capability of making any shape you want. So I modeled this in SolidWorks. It's a 7 millimeter tall pyramid that twists as it works its way up. At least I don't know of any optical function for this, but it's kind of a cool demo part. It shows that I can make pretty much whatever you want. Anything I can fit the tool into, I can make the shape. And we also wanted to push our roughing capabilities. So we went 8 times faster roughing. We went almost the full depth of the tool in each roughing pass. We did each level of this at one depth. Each level was done at one depth. Let's see if this one works. So I spiraled it out, and then I used a traditionally available software. I couldn't define this with an equation, so I just used HSMWorks to generate it. But I roughed it out at these parameters, and then I went back and finished it in one pass. I didn't do additional roughing. I just went straight for the finished pass, and the thing looked pretty good. There was a couple little pits here and there where the IRG-26 is not strong enough to hold a sharp corner. But we showed that. They still didn't seem all that impressed, but I think mechanicals can understand that that was a freeform. I don't think you can diamond turn a 85-degree wall. Well, not that direction. So I've discussed how we've learned what the cutting mechanics are and how to diamond machine, face and mill IRG-26, orthogonal cutting and crystal orientation effects in germanium, how it affects the cutting force, and how it affects brittle fracture, how we generate tool paths, how we correct for our tool, and then a couple of examples of optics that we've made. So we got a couple of papers, ASP proceedings. This paper here, it says in preparation. It got accepted a couple of weeks ago. SERP on the machining of the IRG-26, the orthogonal cutting, and some milling simulations that we did. And in preparation, some more high-speed machining, doing the high-speed machining and not just the orthogonal cutting of the IRG-26, micro ruling in germanium, and this tool area correction are all in preparation. Future work, we want to see how far can we push this material removal rate in the IRG-26 and germanium. If we can go 10 times faster in germanium and get lower forces than we see in the finishing cuts, then it's not going to damage our spindle. We're going to be able to blast through, but is that going to fracture the surface? Is it going to crack it in half? So we want to push those limits. How much can we rough? We would like to prove milling as a rapid prototyper. Advancing dead sharp grooves, explore more of the chip thicknesses at different speeds, see if maybe at lower speeds in IRG-26 could we see a speed dependence. Here's a graph showing that anomalous reading. So when I saw that, it was an order of magnitude bigger than this, so I was like, oh, I was just looking at the decimal wrong, so I just moved on. But it seems like maybe there's something going on here at the low speeds. Also, we see that transient. That to me, the transient force when we're going from a ductile dominated to a brittle dominated, that tells me that's how deep the fracture was, or that's how deep it takes to get through the fracture to the next surface, which either one, once we get to a good surface, once we get to ductile dominated surface, that's what we want to know. So can we use the orthogonal results to predict if we rough at this parameter and finish at this parameter, how deep does the finish pass need to be to completely remove the material? Maybe we don't have to do a semi-finish pass to get through the fracture. Maybe we can go straight from a awful looking surface to a beautiful optical surface in one cut. Also, we've thought of ways we can set up our machine to vary rake while we're cutting, see if we can get like a more continuous change in force due to the rake angle. And then also actually right now today, so it's not quite future work, but they're working on duplicating the orthogonal results that we did, but with an interrupted fly cutting arrangement. And I actually got a text message from John a few hours ago that said he saw a drop in the force between 1 and 1.5 microns. So it looks like we're seeing something pretty cool here. I didn't put them here because it was just a text message, but I thought it was pretty cool. Acknowledgements, Chris Evans, he's been here for everything. Yeah, endless list. Dutterer for teaching me to operate CNC machines. Tom Selesky's been here for, some mechanical and all the optical design's been coming from Dr. Tom Selesky. Meng, Jason did our optical design for the microstructures and for the Alvarez lens. Troutman helped significantly setting up the orthogonal cutting. I was expecting to be here, but orthogonal cutting for the
exciting results.
Yeah, exactly. So, and then Brian Bridges. Sorry, I forgot to fix your name. Brian Bridges. He was working on developing this artifact design when I started, and we've got CPM, 2.6 Foundation, NSF, and I need to include the CFO funded most of the tool area correction stuff, and then a big contributor at Digital Optics Corporation for training and experience and allowing me to come back here and jump right into running the machine instead of needing more training. So that's it. Sorry for holding you guys a little long, but yeah. Question?
So questions from the people here, other than the committee, or the committee if they want to.
I got one. So, when you do this,
You were supposed to ask that earlier.
I've been saving an easy one for you. So, when you do the error correction,
Yeah.
on these parts, do you error correct on top of your artifact, or do you go to a new piece of material?
So
Or can you do either?
So the part we make is the artifact. So we use the same type of material that we were going to then go cut, because if there's any sort of tool deflection or anything like that that's happening more in one than the other, we want to see that. So we use the same, well actually we compared the finishing parameters between what we used and what we would actually need to make a good optic, and we got the same form. So we went with a slightly more aggressive finish parameter for the artifact because it took 25 minutes instead of 3 hours. But it would be in the same material and same depth of cuts for the finish pass, so we can most simulate what's happening statically and dynamically with the tool.
Okay.
We can't measure the freeforms he made. We don't know what they are, so he uses the same correction on them, but we haven't verified that it's correct.
Okay. That makes
So
sense.
in that regard, if you're machining something that inhibits a lot of tool wear, you do your artifact, now your tool is worn, what happens?
Yeah, so the three materials that we picked show negligible tool wear.
Okay.
And so if we were going to try to move into something like silicon or, I don't know, spinel or something that's going to do tool wear, then we would have an issue.
Would you do a different?
But I would still see this as, I mean, when you make the artifact, if you are wearing making the artifact, then either your final optic needs to be a lot smaller than the artifact, or you need to do something different. But I do see this as a way if you could stop an operation, go cut an artifact and measure it, you could see if tool wear was happening and correct it maybe mid process.
This one. So when you're doing your tool correction, you model the position of the diamond relative to the axis entirely as radial error. Do you do anything if it's what we used to call tangential error?
So if the rake face of the diamond is offset, in turning that results in a center defect. In milling, it doesn't leave a feature unless the tip of the tool is past center, and then you'll leave sort of this, I don't know, like you were cutting with a dovetail or something, you leave these funny little scratches in the middle. So when I set up the diamond, I always set the diamond up so that the tip is as close as I can get it to the center, but always making sure that it's past, so that I don't get that feature. But a tangential error would result in a slight change to the shape of the diamond, and it would also give you some radial, it would show up in the radial. So that's why I said we don't correct radial shift and waviness independent, because they're convolved. There's not, I mean, if the diamond is rotated, so if the tip is right at the center but it's rotated, it would look like a diamond that was radially shifted inward.
Mm-hmm.
So you can't really separate them, but if you optimize one and then correct the other one, you get all of it.
Yeah, I was just wondering if your model prediction for your radial correction, because you do one cut, you correct radial and then you don't correct radial, then cut another one, then correct.
I did that,
Okay.
but I didn't need to.
You didn't need to, okay. I would imagine that's because your tangential is pretty good. You know?
Yeah, the tangential, I try to get the static tangential within like 2 or 3 microns.
Because when your
in the camera.
tangential shows up as radial a little bit, that's different than your predicted model of taking out the radial.
Yeah.
Yeah.
So
it's-
with a turning tool, you can shift the tool up or down to fix the tangential or fix the center defect. With a milling tool, there is not a correction that you can make for it. So it shows up as just pure radial. There's no, I don't know that you could correct it. Because it's just it's not orientation dependent, it's always spinning. Yep.
Going to slide 13. If you look at your time domain force data, sometimes when you see that drop off,
13?
yeah, sometimes when you see that drop off, you see large amounts of vibration either
That's
occurring. I don't know if that's causing the drop off or.
You mean this here?
To the drop off, yeah.
You're saying is it an artifact of the dynamometer is what you're saying?
Or if that's what's causing the drop off. I mean, could your tool be vibrating, causing fracture into the workpiece, making that drop?
It's certainly possible, but we are still talking about 50 millinewtons. And we showed, when we were trying to orthogonal cut copper nickel, that we needed pretty significantly high forces to deflect the machine.
But there is an interesting point because I wonder if it's trying to jump back up to the
Is it trying to work its way back
back
up?
to the duct. Yeah, I wonder if there's more. Well, the other thing we noticed was remember in the region where it starts to drop, the force fluctuations even in the average force.
Yeah,
the errors were
some would jump
higher
up.
around that
Yeah.
thing. So I wonder if it's actually.
Yeah, and it could
yeah.
also be if there's some slight
I didn't know
inhomogeneity. I don't know how you would say that, but since the material is unlikely to be perfectly homogeneous, this could be once per rev fluctuations as well.
Would be interesting. to look at
Yeah,
that.
to zoom in on that and see. Yeah, I agree. That would be interesting.
That's interesting. I didn't see that.
Any other questions?
Thanks.
Yeah, thank you very much.
Now we kill you.
Yeah.